The purpose of this third presentation on repetitive loads is to recognize the fact that many processes are coupled in geomaterials. And so we would like to understand what is the nature of the coupling, and then to identify a few examples where coupled processes lead to mechanical consequences due to their repetitions. From a thermodynamics point of view, energy coupling is related to two fundamental concepts. On the one hand, energy is always conserved, is one of the conservation laws, and that comes from Émilie de Châtelet, that says that all forms of energy altogether are conserved. The second one is a principle, a guiding principle that comes from Le Chatelier, and it tells us that nature will do anything it can to oppose change. When we put these two together, conservation and Le Chatelier's principle, we recognize that if we impose a mechanical action, there will be thermal, chemical, and even hydraulic consequences, and vice versa. In other words, a chemical change will cause mechanical effects and thermal and hydraulic. For example, if you take a rubber band and you stretch the rubber band and you touch it while holding it stretched, you touch it with your lips, you will feel that it got hotter. And if you relax it and you touch it again, it will be clearly colder. In other words, there is a clear coupling between thermal and mechanical energy. So all forms of energy are coupled in our materials, and we have to wonder what is the nature of that coupling in geomaterials. And it all starts with the forces that make particles act or move or displace. And when we compute these forces, they are all a function of the particle size, but sometimes related to the perimeter, so to the diameter, sometimes to the area, to the square of the diameter, sometimes to the volume, in other words, the cube of the diameter. And this could be the self-weight of the particle, the weight, the force that the particle carries for being part of a skeleton, which is proportional to the equivalent area it occupies, correcting leaving the porosity outside because somebody has to carry that load as well. The buoyant force, which will be partially lifting the weight, hydrodynamic, the capillary electrical forces, is like when you see that there is dust accumulating on our furniture, even on the vertical surfaces, is because of electrostatic attraction, but it could also be repulsion. And then thermoelastic effects and cementation. Please notice that there are many other forces, and you can go back to a previous recording in which we identified all these forces, but we are only going to focus on these forces for today's presentation. As you can tell, some of them are linear with the diameter, square with the diameter, or linked to the diameter to the third power. Therefore, when we plot them in log-log scale, these are all going to be straight lines with a slope 1, 2, or 3. In other words, the lines are going to intersect. So let's see some of these results. This is the weight of the particle increases with the cube. This is the capillary force, which increases with a linear function. It's a surface tension times the pi diameter to a first order approximation. And this is the force carried by a particle due to an effective stress of 100 kilopascals, which increases with the square of the particle diameter. Because these lines intersect, we can readily anticipate that the capillary force will be more important than the self-weight for particles which are smaller than 1 millimeter. Indeed, you cannot lift an apple that is wet with another apple that is wet. There is not enough capillary force to pick them up. But if the particles were 1 millimeter, 2 millimeters, the capillary force could be enough to pick them up. And that is the limiting size for sandcastles. Capillary force gains more importance than the effective stress, 100 kilopascals of effective stress, when the particles are in the order of a few microns. And therefore, we see the importance of capillarity for fine-grained materials. For electrical forces, the analysis is more difficult to do. You may refer to the earlier presentations on this topic, but we can think of what are the consequences of changing a clay saturated with fresh water with seawater. Let's say that there is saltwater intrusion. What are the consequences? And well, there will be contraction because of reduction in the double layer repulsion. And that contraction will increase as the particles are smaller and smaller. Therefore, it appears that electrical forces gain relevance when they are about 1 micron to 10 micron in size. With this in mind now, let's start in fact with the effect of exchanging the pore fluid, and we are going to do cycles. And so here we go. On the left-hand side, you see now relatively old molecular dynamic simulations. You see the counter-ion cloud and the clay layer, the phyllosilicates, and the additional water in between the clay layers. We're going to exchange the ionic concentration of this water to increase and decrease the double layer repulsion. In other words, we're going to be changing what we called earlier the DLVO interaction between these two parallel particles. In general, we can see that for silica flour and for sands, etc., as the specific surface gets smaller and smaller, the potential strains are going to be very small. These are based on pure computations using the DLVO theory, and it gains some relevance for the kaolins. Kaolins are large clay particles, but they become particularly important for bentonite, where we have a very high specific surface. We can also recognize that the higher the initial stress, now the clays are highly compacted, you are fighting against the effective stress. So as the effective stress increases, the potential strains are going to decrease. With that in mind now, let's do the following experiment. We're going to use a kaolin, because if we do it with bentonite, the advective flow is so slow that instead of taking 2 years approximately for this test, it would have taken 20 or 100 years, prohibitively long tests. To avoid that, we do it with kaolin, and we use 2 containers, one with deionized water, the other one with brine, and a switch here that will allow us to flip from deionized water to brine without changing the pore pressure. And that is very important, because if we change the pore pressure, we change the effective stress, and if we change the effective stress, there will be volumetric changes. So we don't want to change Terzaghis effective stress. The overburden, the weight is constant, and the pore fluid pressure at the bottom will be constant. The only thing that will be varying will be deionized water versus brine, and these are going to permeate through the specimen. We will measure the volumetric deformation by using an LVDT sitting on the top to see whether there is expansion or contraction. When we do the first injection of brine, which is in red, there is contraction. Then this is not very clear because it's the first cycle and we are fighting the side friction, but as the other cycles become more regular, let's put emphasis on them. As we inject brine for the second time, there is additional contraction. When we inject deionized water, it expands. Contraction, expansion, contraction, expansion, contraction, expansion, reaching pretty much an asymptote relatively fast within 1, 2, 3, 4, 5 cycles. Once again, these tests are very lengthy because you have to allow for complete fluid replacement, which in this case we were monitoring with the effluent as well as with these electrodes at mid-height. Summary: just by changing the pore fluid without ever changing the pore pressure or the load, we see the succession of contractions and expansions that are taking place towards an asymptotic value. Once again, we see the idea of an asymptotic void ratio, terminal void ratio, in this case triggered by chemical cycles. Now let's explore thermal cycles. If you go back and you look at the forces caused by thermal expansion and contraction, is proportional to the thermal expansion coefficient, the change in temperature, and the diameter square. Now, the forces created by effective stress are proportional to the area that the particle occupies, which is also diameter square. So when we do the ratio of thermal forces to effective stress, induced forces, the diameter cancels out. That means that thermal effects from the point of view of mineral expansion and contraction, not from the point of view of double layer changes, which is also affected, but this is just because of mineral expansion and contraction, is grain size independent. If that is true, we should see thermal effects not only in clay, silt, sands, but we should even see it in large blocks, rock blocks. And that is the way I'm going to demonstrate it, which is with blocks of rock. So it doesn't look like a sediment study, but just think of it as very large grains to demonstrate the effect. And so this is the concept. And we see that many times mountains are gradually failing without having been subjected to seismic activity or heavy rains. And so what is going on? Well, this is the hypothesis. When it gets very hot, the block expands towards the free space, but when it is colder, contraction is such that allows the choke blocks to fall behind. So during the next cycle, it expands further out. During contraction, the choke blocks come down, and gradually we can see that this big rock block is moving forward and displacing in a ratcheting mode. And then we wonder, do we see this in nature? And indeed, you will find these analogs wherever you walk in the mountains. Look at this wedge on the Eugenia Canyon, and you see this wedge is going down, and the resisting block is already tilting up. This is not a toppling mechanism. This is really the successive wedging due to thermal expansion and contraction. And we keep seeing these wedges around. This is in the Grand Canyon. And if you see Masada Mountain, some of the blocks are falling off. There has been extensive monitoring. You see the deformation gauges here, and there is another one at the top. But most of all, I would like you to recognize that here are the choke blocks falling behind during every contraction, during cooling. And another example, this is in Alula, and you see that there has been a significant displacement here at the base, where this layer has been interrupted. And when you zoom in, you not only see the displacement, but you also see the choke blocks. Can we simulate this in the laboratory? Yes, we can experimentally test it. And this is the case. You see the resisting block at the front, the choke block in the back, with a certain angle, with thermocouples, a heater, and a fan to homogenize the temperature, with an LVDT that is tracking the position of the choke block. And with every heating and cooling cycles, the choke block keeps going down, and the front block keeps moving forward. We can analyze this situation. We can wonder what is the maximum force, frictional resisting force at the bottom of the block. And then we can see the compatibility of displacements, typical mechanistic analysis, equilibrium and compatibility. And there are two displacements, one caused by the thermal expansion of the block, but that creates also a force that squeezes the block. So there is a stress-induced contraction of the block. So this is the effective deformation of the block. And we have to compare that one against the threshold deformation for friction sliding, which will depend on the rock roughness and other rock mineralogical characteristics. What is the thermal expansion? Is the thermal expansion coefficient, the temperature, and the depth that the heat front has invaded, which we're going to call the skin depth. And twice because it's hitting all around, so it's affecting at the front and also at the back, where the choke blocks are falling. And that skin depth is a diffusive process, so it's going to be the thermal diffusion coefficient times the exposure time, whether it is 12 hours or 6 months, a seasonal cycle. The formation due to stresses is the force times the width, and this is time divided the Young's modulus. And so this is going to be the deformation that the block will experience. So when we put all this together, now we can come up with an equation. In fact, we can recover what will be the thermal temperature change that is required to cause permanent displacement. And you see how the interplay with the different variables. The last expression is to see it more readily, where we have made the slope angle 0. It cancels out in this force equilibrium equation. The two go to 0. And so now we have a very similar expression. The higher the threshold deformation to cause permanent displacement, frictional displacement, the higher the temperature that we will require to reach that point. And conversely, the longer the exposure time, whether this is 12 hours or the seasonal fluctuation, the lower the thermal oscillation. From our studies, and for the case histories that I showed earlier, it appears that seasonal oscillations are the ones that are really governing this ratcheting accumulation in massive rock blocks in mountains, because there is the need to have enough time to penetrate the rock to magnify the expansion that it experiences. Now, the same is going to happen in a pile. So imagine we're looking for the soil pile interaction, and this is a segment. This segment, we can analyze it now piecewise because of equilibrium, the force coming throughout the pile at the top and at the bottom. The difference between them is how much it has been mobilized in terms of the shaft resistance. And the shaft resistance is the mobilized shaft times the shaft area, which is the perimeter times the length of this element. And the mobilized shaft resistance, we're taking a linear function with respect to some threshold value for the elastoplastic deformation of the shaft resistance. Once again, we have compatibility of deformations, which is the thermal expansion of the pile and the contraction of the pile due to stresses. And when we put all this together, now we can begin analyzing what will a pile experience when we heat it all along the shaft with tubes that run through them in order to use them as energy piles. In other words, to store heat during the summer and conversely, to pull low temperature fluids during the summer and re-inject cold water in the winter to pull out the stored heat for building heating during the winter months. When we analyze this soil pile interaction process, including the thermal changes, now we begin to see what happens, that this is the distribution of the axial load with depth for a pile which is 20 meters long and that has the shaft resistance, the ultimate shaft resistance, the same as the ultimate tip resistance. So this is a mixed shaft bearing and bearing pile. For an intermediate case, this is the distribution of side resistance. The relative displacements that have occurred are more pronounced at the top than at the bottom. And we see what happens with different number of cycles. By the time we reach the 50th cycle, the load distribution has changed, not pronouncedly, but it has changed. And we have to analyze what happens during the heating cycle and during the cooling cycle. And because it has, in fact, more differences than the accumulation that otherwise would be observed. Once again, in this case, in terms of the relative displacement, we see during heating that there is expansion of the pile head, while during cooling there is quite significant contraction. The take-home message from this is that for piles that have a relatively good factor of safety against bearing capacity, we are not going to see ratcheting taking place. All these changes are going to be seasonal changes with the cooling and heating cycles, but we are not going to have gradual burial of the pile. A caveat to this is that this analysis only looks at the thermal expansion of the pile. However, the sediment itself is going to experience other changes. The pile radial expansion and contraction is going to change the shaft resistance, and thermal effects on soils, as we discussed earlier, may also lead to changes in the state of stress. So the problem is, in fact, more complex than this simple thermomechanistic analysis. We see these thermomechanical coupled processes not only in rock masses, in piles, look at in geomembranes. They are exposed during construction, and because of heating and cooling cycles, now there is a downward displacement of a plastic liner inclined on a surface. And this is exactly the same mechanism exceeding the threshold for a frictional deformation and gradually accumulating, leading to all these wrinkles that can be so negative for the long-term performance of these liners from the point of view of very effective conductive paths that you may see in Kerry Rowe's ranking lecture, for example. Now, there are other effects for the thermomechanical coupled processes, and one of them that is quite pervasive is thermal cycle. And with climate change, regions that were not subjected to thermal freeze-thaw cycles are going to experience them. And I think that, or we're already seeing them, there will be increase in instabilities that otherwise, in locations that were otherwise stable throughout history. So we can run this in a triaxial test with a deviatoric load imposed with a pneumatic cylinder, so it's very constant. And then we have a cooling, a loop with a refrigerant to create cooling and heating cycles. Let's see some of the data. The upper one is for a sandy material. The lower one is for kaolin. In the upper one, we see that during cooling, there is supercooling, which goes below zero. There is a thermocouple at the center of the specimen. There is supercooling, and then all of a sudden, phase transformation takes place. It goes to the phase boundary until the whole material freezes up, and then it continues cooling. Well, during warming up, the opposite occurs. We begin warming up, we reach 0 degrees, melting occurs, the temperature remains constant until all the ice has melted, and then it continues warming up, and we see what happens with the multiple cycles. With kaolin, it's a little bit more complex, and you see that instead of remaining constant during phase transformation, the temperature continues decreasing during phase transformation. There is also the supercooling, the jump at the beginning of phase transformation, but then the gradual freezing is affecting smaller and smaller pores, and we see that the temperature changes. And what is actually happening when we see this through the eye of a macro CT is that we are also forming ice lenses. There are no lenses in the sand. In other words, the ice grew from pore to pore to pore, so it was pore invasive. However, ice segregates in clays, in fine-grained materials, and is grain displacive. It pushes grains out like a carrot growing into the formation. In fact, it's exactly the same physics, and forms these ice lenses. And this will have huge implications because during thawing, this material where freezing was pore invasive going to pore is not grain displacive. So then when you thaw it, the fabric may not be altered. However, if it was a grain displacive growth in fine-grained materials, during thawing, these ice lenses become water lenses, and first of all, the shear strength decreases dramatically. But in addition to that, the cryogenic suction during freezing consolidated the clay around, and during thawing, that consolidation has a permanent residual effect. It doesn't swell back. Please look at the publication to track the data carefully, the results. But the important thing I want to say is be very careful if it is going to be grain displacive, because it can be very negative, particularly if there is a biasing deviatoric load. In other words, if the initial stress is not isotropic, which is never the case in soils, then if there is a biasing stress or in a slope, these are going to lead to very pronounced shear displacement. The key parameter to use to recognize whether there will be grain displacive or pore invasive is to compare the surface tension, those 72 millinewtons per meter, to the effective stress times the particle diameter. And so if the effective stress is large and the particle diameter is large, then this ratio is small and it will be pore invasive. Otherwise, we really have to be particularly careful. Now, the other case that is quite common in soils everywhere around the world, that above the water table, the soils are going to experience wetting and drying cycles. In other words, there will be cyclic suction in the soils. And now we have to think what happens, but we do know that there is progressive damaging of slopes because of wetting and drying cycles. So we can explore that once again with a pneumatic cylinder in a floating odometer cell with thermocouples and bender elements to monitor everything, to gossip what is happening inside the specimen so we can better understand the processes. And let me just show you one data set, which is the case of a kaolin that is initially loaded to 50 kilopascals and then is dried to create a suction that will be equivalent to 500 kilopascals, and then wetted again and dry again. And we don't show all the lines, but you can see how with multiple cycles, the specimen continues contracting. Started with a void ratio of 1.15, and now we are at a void ratio of less than 0.8 because of successive wetting and drying cycles. This one started at 50 kPa, this one started at 100 kPa, and it was subjected to the same suction. Now, when we plot the evolution for those 30 cycles, these are very long tests, when we plot the evolution of void ratio at the end of wetting and at the end of drying, these are the trends. Once again, we can fit it with the empirical models that I had shown earlier in the first presentation of this series to anticipate what is the terminal void ratio during drying and the number of cycles that is required to reach half of that quantity. So in this case, it takes very limited number of cycles, 7 cycles for half of the process to terminal void ratio, and then it decreases gradually to the terminal void ratio. But it can have very pronounced effects. Suction is very powerful. The other consequence is that if I take a specimen and I measure the soil water characteristic curve, that means the saturation, gravimetric water content, in this case, it could have been saturation versus suction in order to compare. For these two cases, it's better to use the gravimetric water content. This is the material during the first cycle. This is the first time that is being dried in order to determine the suction saturation curve. This is after being exposed to 10 cycles. And now we can see that if we identify the air entry value, the air entry value has changed quite significantly because the larger pores have been contracted. It's not affecting the smaller pores, which controls the higher suction values. And nuclear magnetic resonance data confirms these effects. So it's time to conclude. Well, we have already been saying that in the previous presentations. You have to anticipate the consequences of repetitive loads in all types of natural and engineered systems. And what I added today is that these are often triggered by coupled processes, hydrothermo, chemomechanical coupled processes. In these multi-physics cycles, chemomechanical coupling, chemomechanical, may become a concern when you have specimens with less than 10 micrometers in particle size. In other words, where we go into the clay-sized particles, which are actually, in most cases, clay minerals. If you want to have another indicator, think of materials with a specific surface greater than 1 meter squared per gram, or with liquid limits greater than 35. Those are the characteristics of your material. Chemomechanical coupling may be very relevant. For example, this is going to happen all around the coast with saltwater intrusion exacerbated by sea level rise. Thermomechanical coupling, remember the dimensionless ratio, the size of the particle cancels out, so it's grain size independent. For suction cycles, you may go back and take a look at when capillary forces become more important than gravimetric forces. This is in particles that are smaller than 1 millimeter. But if the material is subjected to higher stress, minor changes in suction are not important. So look at the potential changes in suction compared to the effective stress under saturated conditions. If this is high, then you have to be concerned with the hydromechanical effects of suction cycles. What about freeze-thaw cycles? They are going to be most critical in grain displacing materials. So when ice formation displaces grains, and that will happen when this ratio is large. In other words, when the particles are small or the in situ state of stress is low. And in all cases, remember that volumetrically speaking, all these processes are going to drive our materials towards terminal void ratio or terminal density. And if the materials are subjected to an initial obliquity, for example, if they are beneath a loaded footing or on an inclined plane, the probability of ratcheting will increase with a degree of obliquity in the state of stress. For additional information, you will find examples and details in these references.